Hello, let me discuss today. Is it logical to consider failure strain in flexure compression as 0.0035 for high strength concretes? So let us see. Now, if we see the typical stress strain curve for concrete in compression obtained from laboratory, we will get such curves. So here on y axis there is stress in Newton per mm square, and on x axis there is strain. So these are the graphs obtained for different grades of concrete, where on the x axis the strain is mm per mm, that is decrease in length due to compressive load divided by original length. So these are all the strains indicated up to failure: 0.001, 0.002, 0.003 and 0.004 compressive strains. And here on y axis these are the compressive stresses, 10 Newton per mm square, and it is increasing, and these are the various curves. Okay, now we can see here from this laboratory stress strain curve obtained by conducting the experiments on concrete cylinders, that for various grades of concrete, that is starting from lower grade to the higher grade, the peak, that is the maximum stress, is almost indicated at a compressive strain of 0.002 for almost all the grades. And then at the end of the curve it indicates the failure strain. Now going further, however, we all know that Indian Standard 456 2000, that is a code for plain and RCC concrete design, it has not adopted the laboratory curve as it is because of the difficulties involved, and therefore as per the convenience and comfort they have modified the curve and they gave an idealized stress strain curve for concrete, which we use for design, and it is given in clause 38.1 of IS 456 2000. Now let us see it in briefly. Now again here it is stress and strain. Now up to 0.002 strain, now it is a parabolic curve as per IS code, and instead of the descending branch of the curve like whatever obtained in the laboratory, the IS code assumed that from 0.002 up to 0.0035, that is up to failure strain, it remains straight, and this is FCK, that is characteristic compressive strength of 150 mm by 150 mm by 150 mm concrete cube after 28 days of curing. So that is FCK, characteristic compressive strength. But then this curve dips down and it becomes 0.67 FCK. Now let us discuss a short story how this 0.67 appears here in brief. Now what happens is that we conduct the test on the concrete cylinder in the laboratory, whose size is only 300 mm height and 150 mm diameter, or sometimes 200 mm height and 100 mm diameter, and moreover we compact it well, the quality control is good, and the load applied at a certain rate on the cylinder in the laboratory is for short time. But if you look at the site, when you actually do concreting on the site for column, beam, or for that matter any element, then the load applied is not short, it is for a lifetime, it is a sustained load, and moreover the size is more, and then there is a quality control issue, and therefore people across the world, they said that the concrete technologists, that normally the strength of concrete on the site in any structural element divided by strength of cylinder in the lab is normally 0.85. Then why it is 0.67? Now let us discuss further. Now again it is a well established fact that the compressive strength of cylinder divided by compressive strength of cube is normally 0.8. That means the strength of cylinder is normally 80% of that of the cube, and therefore 0.85 into 0.8, cumulatively it becomes 0.67 FCK, and therefore instead of FCK the curves dips down. One more time the curves dip down, that is finally again it dips down, because this 0.067 FCK, again we have to divide by gamma m, that is partial safety factor for material, that is for concrete, as per limit state method given by IS 456 2000. And therefore we know that for concrete we take partial safety factor as 1.5, and therefore again it becomes 0.67 divided by 1.5, that is 0.45 FCK. So here that means this is a final curve, we use it for design in flexure, that is in bending. So 0.002 is the strain, and up to which it is a parabolic variation, stress is parabolic, and then it remains constant, but whereas strain increases, and 0.0035 is the failure strain. Now if we look at the strain distribution diagram as per limit state, now let me consider one rectangular beam of width B and overall depth D. AST is the area of tension steel, so it is a singly reinforced beam, and D is the effective depth, that is from the top fiber up to the center of the tension steel. Now this is a strain distribution diagram. Now here it is a neutral axis, so here it is a neutral axis here. Now here we know that the failure strain is 0.0035. So assuming that this rectangular beam is simply supported, we know that above the neutral axis there will be compression, and below the neutral axis there will be tension because of sagging action, and therefore we can say that 0.0035 is the strain due to bending, but it is a compressive strain. And here of course 0.002 already we have seen it. Now below the neutral axis, this is the level of steel. Here the strain is 0.87 Fy upon Es plus 0.002 in the tension steel. So this diagram is nothing but the strain distribution diagram for singly reinforced beam as per limit state theory given by IS 456 2000 for balanced condition or critical condition. Balanced condition means we all know that they assume that when the beam is balanced in nature, then the steel and concrete, they undergo failure simultaneously, that means at the same time. Whereas if the beam is under reinforced, the steel will fail first, and if the beam is over reinforced, the concrete will fail first. But let us not go into detail into that, because that is not the point of my discussion here. Now here let us see what is the strain here. Now from the derived definition of strain from strength of materials, we know that basically strain is stress by Young's modulus. So it is Fy by Es, where Fy is the yield strength of steel, so it is Fy by Es. But then 0.87, as we all know, it is a partial safety factor for material for steel, and therefore it is 0.87 into stress divided by Young's modulus. But plus 0.002, let us see how this 0.002 appears here. Why it should appear? Actually because the derived definition from strength of materials is strain is stress by Young's modulus, then as per IS code 0.87 will come, but why 0.002 has to appear? So let us see a bit of that before we go to next point. So here this is the characteristic and design stress strain curves for HYSD bars. Now what IS code says is, of course there is an idealized curve, it is not the lab curve. So again it is stress versus strain for steel. Now for mild steel, we know that in strength of materials, when we test mild steel bar, then it is possible to locate the yield whenever the steel gets yielded, that means upper yield point or lower yield point. But for HYSD bars, that is high yield strength deformed bars like Fe415 or Fe500 or Fe550, it is somewhat difficult in the lab to locate the exact yield point, and therefore what IS code says that this is the characteristic curve, that is Fy, for example Fe415. So here you can see 415, but then because of partial safety factor the curve has dipped down, so it is a design curve as per IS 456 0.87 Fy. So it is an idealized curve, it is not a lab curve. Then what they say, since it is difficult to locate the yield point, they say that at 0.002 strain, you draw one line parallel to the original curve, this line. So one line is to be drawn, and wherever it intersects the design curve, you take it down, and the strain corresponding to that will be 0.87 FY by ES plus 0.002. So you have to add this 0.002. Okay, that is beyond the that means that is the yield point they assume, because it is difficult to locate the yield point. So they assume that 0.002 that is a strain in the body of the steel. Already that much strain in the body of the steel. Sometimes we call it as a permanent set. Now, and that is the reason why here 0.002 appears. Now let us see that what happens next. Now here this is the neutral axis. Now from here to here it is XU max, that is the depth of balanced neutral axis, and from here to here it is the effective depth D, and therefore if I say XU max by D, that means XU max, that is the distance from the top compression fiber up to the neutral axis divided by the effective depth, then I can easily write from equal angle triangle property that XU max divided by D is 0.0035 divided by 0.0035 plus 0.87 Fy by Es plus 0.002. But IS code again says that for all grades of steel we should take Young's modulus as 2 into 10 raised to 5 Newton per mm square, and therefore when I do substitute this value of Young's modulus in this equation in place of Es, then what happens is XU max by D is equal to 700 upon 1100 plus 0.87 Fy, and therefore XU max, that is the depth of neutral axis in case of balance section, is 700 upon 1100 plus 0.87 Fy, the whole multiplied by D. That means by putting the value of Fy, grade of steel, maybe Fe415, Fe500 or Fe550, that means any HYSD steel, okay, we can obtain the depth of balanced neutral axis in terms of effective depth. Now, but let us have once again the let us have a look at the stress strain curves. Now, though IS code assumes that the failure strain is 0.0035 for all grades of concrete, because if you look at this equation, it is independent of grade of concrete, whether it is M20, M60, M100 or M120. Okay, as per IS code, the failure strain is 0.0035 only for concrete, and therefore this depth of balanced neutral axis is dependent on steel only. Of course it is dependent on concrete, but that 0.0035 is taken constant for all the grades. Independent of grades, it is taken 0.0035 only, and therefore in a way it depends on grade of steel only as per IS code. But now if you look at this curve, as I was saying, that as the strength of concrete goes on increasing, your failure strain goes on decreasing, because you can see here that for the lower grade of concrete the failure strain is more, and as the strength of concrete is increasing, your failure strain is less. That is because the lower grade of concretes are more ductile, that means they undergo more strain before failure, whereas as the strength of concrete goes on increasing, the concrete becomes less ductile, rather it tries to become more brittle. And nowadays we know that in cities like Mumbai, or for that matter many metropolitan cities across the world, in the skyscrapers and the infrastructure projects, the grade of concrete, even they are using M100, M120 like that, but still we are using the strain of 0.0035. So suppose for example, if we use M80, M100 or M120, that means the concrete will try to become more brittle. So it will show the strength as more, but the failure strain will be less. So what I will do, that instead of accepting whatever IS code says, what I will do, that I will assume that I am using some high grade concrete, maybe M100 you can assume, and randomly I will assume that my failure strain is 0.0025. I will not accept IS code's proposition. Instead of 0.0035, I will take it as failure strain as 0.0025, because the strength of concrete I am using in my building is M100, maybe for skyscraper or some important project, and therefore I know that from the experiments across the world, I know that concrete tends to be more brittle and therefore I will take the strain as 0.0025. Okay, now what happens again? Of course this will remain same. Now again if I work out by taking this strain of 0.0025, then xu max by d, again it will be same, but instead of 0.0035, now I will put 0.0025. Now again when I put TS equal to 2 into 10 raised to 5, now xu max equal to 500 divided by 900 plus 0.87 Fy into d. So as per IS code, independent of the grade, it was 700 divided by 1100 plus 0.87 Fy into d, whereas as per our random assumption of the 0.0025 strain, that is less failure strain for high strength concretes, it is 500 by 900 plus 0.87 Fy into d. Now let us interestingly see what is the practical implication of this. Now what I will do, that I will take these three HYSD bars, that is Fe415, Fe500 and Fe550. Now as per IS code, that is which is independent of concrete grade, the equation for xu max, that is depth of balanced neutral axis, will be 700 upon 1100 plus 0.87 Fy into d. So when I substitute Fy is equal to 4 on 5, then it will become 0.48 d, that is value of the depth of balanced neutral axis. When I substitute Fy is equal to 500, the depth of balanced neutral axis becomes 0.460. When I substitute Fy is equal to 550, the depth of balanced neutral axis is 0.44 d. But this is as per IS code. But as per our discussion, randomly whatever we have seen by taking 0.0025 for HSC, that is high strength concrete, our formula is 500 upon 900 plus 0.87 Fy into d. So when I substitute Fy here as 4 on 5, it will be 0.39d, and for Fe500 it is 0.37d, and for Fe550 it is 0.36d. Okay. Now what I will do randomly, just to understand the practical significance of that, I will consider one beam, a rectangular beam, whose effective depth is 500 mm. And once we will apply this formula, and once I will apply this formula, and what will happen I will see. So as per IS code, the depth of balanced neutral axis xu max will be 240 mm, because it is 0.48 into 500. Okay, whereas for high strength concrete it will be 0.39d, that is 195 mm. Again for Fe500 it is 230 and 185 respectively, and again for Fe550 it is 220 mm and it is not 220 here, 0.36 into d. So let me do 0.36 into 500. So it is 180 mm. So it is 180 mm. So here we can see that for different grades of steel, as per IS code we get certain values, and if we consider the failure strain as less for high strength concrete, for example randomly by considering as 0.0025, then we get the depth of balanced neutral axis as less than that obtained by IS code method. That means, suppose I have a rectangular beam of effective depth 500 mm, then as per IS code, if my actual depth of neutral axis is more than 240 mm for Fe415 steel, then it will become over reinforced. Up to 240 mm the depth is permitted, but for high strength steel, as per our discussion, it is only limited up to 195 mm. That means if the depth of actual neutral axis exceeds 195 mm, then it will tend to become over reinforced. Similarly, similar discussion can be done on the similar line for Fe500 also and Fe550 also. See, so here I want to make one point very clear, that nowadays with the discussion of earthquake engineering being a very important topic all over the world, and moreover the skyscrapers and other infrastructures, people are using high strength concrete, and high strength concretes are more brittle, and in earthquake engineering ductility is one of the important considerations, rather it is the most important consideration. And therefore, but still IS code says that for any grade you use the failure strain as 0.0035, but here if you go for high strength, then the beam which is under reinforced as per IS code becomes over reinforced. that means it becomes less ductile as per this our discussion. And therefore one has to really think over this. There is a scope for research in this area, but again I am not coming to any conclusion with this discussion, because again interestingly what happens is, whether it is 0.0035, 0.0025 or any other strain value, these all strain values are obtained by conducting experiments on plain concrete elements in the lab. Okay, whereas in RCC we don't use plain concrete, we use concrete plus steel. So again we should know the interaction between steel and concrete. So coming to conclusion is again very difficult, but just I wanted to make it clear that there is a scope in research, or maybe at least I wanted to provoke a thought that instead of considering 0.0035 for all the grades, it is better to consider the failure strain as lower than that of lower than 0.0035 as the strength of concrete goes on increasing. Thank you.